In this challenge, we're going to look at how Virtual Crash handles basic kinematics, and I'll show to you that Virtual Crash is doing exactly what you would expect a physics simulation software package to do. There are no mysteries, no surprises. So let's start by using our trial version. And again, you can download this at our site, www.vcrashusa.com. Let's draw a coordinate axis. And let's do a little editing using our left side control panel. The units are in feet. I'm going to set it at 0, 0. I'll set the origin at 0, 0, and let's freeze it. So we see our ticks placed every foot, and we have our labels every 5 feet. Let's put a car onto this scene. Now you can do these same studies with the 3D geometrical objects. You just make them rigid bodies, and I've shown how to do that in other videos. Today we're just going to use our vehicle model, which for the trial version you're only allowed to use a single type of vehicle. Sorry, it's a trial version, not the full version. If you want to purchase the full version, feel free to contact us at sales@vcrashusa.com. Now let's place our vehicle at 0, 0, so that's the location of its center of gravity. And what I'm going to do is I'm going to rotate it to arbitrary orientation, so its heading is pointing in just a random direction, nothing special. And we could start to mathematically model based on standard accident reconstruction principles and basic physics what we would expect this car to do as a function of time. So let's go ahead and give our vehicle an initial speed. And you know, I'm just going to pick 34 miles per hour. Why not? Perfectly random. And let's change the color of this guy just because I feel like it. And in the contour view, it allows us to kind of see through the vehicle a little more clearly onto our XY plane. And let's play it versus time. We could see the car moving off in a straight line trajectory at a constant velocity versus time. Now, how do we know that Virtual Crash is putting that car shape where it should be in our XY plane as a function of time? Well, why don't we go ahead and let's just model it. So first let's go to our whiteboard. If you've watched our videos on our site by now, you know I love the whiteboard. So of course the vehicle is just at a constant velocity. We expect that the x position as a function of time is just going to go like its initial x position, and I'm gonna use a subscript I instead of not, so I don't get hate mail from some of you. X sub I plus the x component of the velocity times I times t plus 1/2 the acceleration component in the x direction times time squared, and I'm assuming implicitly that the initial time, and I just did it again, I put not. That is a habit of being a physicist. Sometimes we like to use nots. The initial time I'm automatically assuming is at 0, and we have the same equations for the y component of the vehicle's displacement. And I'm just going to keep these up here because I'll keep referring back to them. At constant velocity, we know obviously that there is no acceleration. So those guys are 0. And I have intentionally placed the CG position at 0, 0. So we can simplify our kinematic equations as follows. Times time times time. And of course the velocity is a vector, and so it's in this case we're constraining the vehicle to move along the XY plane. I didn't draw an XY plane. That was terrible form. So here's our XY plane. Our vehicle is constrained to move, in this case, along the XY plane. Although you do have the Z degree of freedom, vCRASH is a fully 3D physics simulator. But in this case, we've constrained it by construction to move along the XY plane only. And so our X component is given by the magnitude of our velocity vector times the cosine of our heading angle. In this case, there's no slip angle. So whatever we set for our vehicle's yaw is going to correspond to theta. Let me draw that here. Here's our velocity vector, which I randomly chose. And here's theta. And the y component is just simply given by the sine. And hopefully everybody's okay with this. Let's go to my favorite tool, Excel. Spreadsheet. And we'll have an entry for theta in degrees. And let's just set up our time columns. I'll just do this on 1 second increments, just to make life easy. And you know what? I'll break the components down here just for convenience. X as a function of time, y as a function of time, and we can calculate the total distance as a function of time. It's pretty trivial. Now, nobody is online to remind me what I set the initial conditions to, so I have to look it up. So I use 34 miles per hour. And I set yaw, the heading, to 23 degrees. And now we're just going to do a little decomposition. And hopefully you're familiar with how to do this on your own, but you can follow along. So our x component of the velocity vector is 31.3 miles per hour, and the y component is about 13.3 miles per hour. And again, this is how we're modeling our kinematics here with these two equations. So let's just go ahead and use them in our spreadsheet. Sorry. We need to convert our velocity into feet per second. I highly recommend that unless you enjoy making lots of errors in your calculations. I do not. And we're going to multiply that velocity x component by time. And hopefully this works. Alright, so those are the expected positions of the vehicle's x component as a function of time. And now let's do it all over again for the y component. And we can even calculate the total distance in a trivial way here because it's just straight line motion. So all we have to do is take the sum of the squares of the x and y positions here. For a little more more complicated situations, we have to be a little more careful. But in this case, we can just simply do this. And this will give us the total distance traveled as a function of time. Okay, so here is what we expect to happen. And we can plot these. If we want it to be extra nerdy, here's x position versus time, and y position versus time. And you can see they're straight lines. Actually, I'm just going to plot these as straight lines for a reason. Okay, so let's start sampling where virtual crash is placing our vehicle as a function of time. There is a log file printout capability where you can look at the position and orientation of your objects in virtual crash versus time. That's been disabled for the trial version, sorry, but it's not hopeless. One simply looks down here while you're sliding your vehicle around, your object around on the scene. And that's one of the other neat things about virtual crash. Once your object's selected, you can move it around along the interpositions that are shown in the gray boxes that are moving along diagonally. And it'll show you the position of whatever object you've selected. Actually, it'll show all the objects in the scene for each moment in time as you're sliding your mouse cursor along. So look down here, and we'll just start sampling some points. Obviously, the position is at 0, 0 for time equals 0. So that's pretty simple. We're going to set up our observations now. That's our mathematical model. And here are our observations. So 0, 0, 0. Wow, that was very simple. And let me make my life a little bit easier by looking at both programs simultaneously. So I'm going to set my next sample point. I just randomly picked it with absolutely no thought behind it. I had to pick something, so I'm just picking this point. And that's at 9.36 and 3.973. And I'm just going to randomly pick another point without much thought behind it. And you move it along the interpositions, and then you just kind of click on the spot you're curious about, and it'll put the data down here. So I've chosen time equals 6.38 seconds. Excuse me, 0.638. And x is equal to 29. I'm just going to stop talking now. I'm just going to pick one more point. I think we might be beating a dead horse here. Just way out here. Okay, I think we've got enough data. So here's what I'm going to do. I'm going to make a graph of each of those, and I'm going to try to superimpose it onto our model. And there you have it. The x position, our observed points or positions on the x-axis, these little blue dots here, sit right on top of our model's orange line. And we could even be more fancy and do a linear fit to the data, and we should be able to get the x component of the velocity vector, which, let's get it in feet per second here. (45.90251), and our fit says the x component was 45.903. I hope that's close enough for you skeptics out there. And now let's do the same thing for y. So here is our plot for our observed data points, and here's a line for a model, and we see again for the y component, the blue dots from our observations are sitting right on top of our orange line, which is from our simple kinematic model. No surprise, and if I had sampled more points, of course, they would have just filled in on top of the line, orange line. And again, let's do a fit for you super skeptics out there. We do a linear fit to our data. And let's again convert our velocity along the y direction, the y component velocity, into feet per second. So our fit should say 19.48446, and we have 19.484. So pretty good. I hope that's good enough agreement. One last little piece of business is the total distance. Total distance traveled, although I don't think this is going to be too much of a surprise. Now, I read the total distance off of the calculation from vCRASH. I did not calculate it from the observations. So this is coming directly from the output from vCRASH. So it is interesting to look at. And let's change that orange line again. Okay, so here's the total distance traveled as a function. Total distance traveled on the y-axis, time on the x-axis. And again, we see the blue dots that we read off, that we observed from vCRASH, sitting on top of the orange line, which is from our kinematic model. And let us again do a fit. And because the motion is purely linear here, the fit coefficient is just giving us the total velocity, or the magnitude of our velocity vector, which we had at 34 miles per hour. Let's convert that to feet per second. And 34 miles per hour is 49.867 49.867 feet per second. 49.867 feet per second come from our fit. And so once again, we see in the case where there's zero acceleration, just straight line motion, virtual crash is doing nothing mysterious. It's doing everything one would expect it to do based on kinematics. Next time we'll do a case where we have uniform acceleration and uniform deceleration. I encourage you to try your own tests and experiments and convince yourself that this product is a physics simulation tool that can be used in accident reconstruction. There is no mystery. Virtual Crash is a great product. Try it for yourself, then buy a full license. Visit us at www.vcrashusa.com. Watch our other videos. See what this software can do. Thanks for watching.